Hey, I'm David. I'm one of the lecturers at the Maths Learning Centre, and this is a video about finding matrix inverses. So in a lecture I did earlier, I talked about matrix operations, and matrices were a mathematical object that an array of rectangular array of numbers, and we were able to do all the algebra things that we were able to do it with ordinary numbers, except some of them weren't quite so easy. And so we were able to do addition and subtraction. There was a zero. There was a thing that when you multiply it by things keeps them the same, the way that 1 works, and that was called an identity. There was a few extra things that matrices do that numbers can't do because they're not big enough. And then there was this final thing, which was the inverse. And the inverse was the matrix answer to division. There is no such thing as division for matrices, but there was such a thing as being able to find an inverse which would allow us to solve multiplication equations. So we were able to solve equations like A times what equals B to find out what the what is, which would normally use division for with numbers, but we don't have division, so we have inverses. And the definition was this. Here's an n by n matrix. Then an inverse for A is a matrix which is denoted by A inverse, such that A inverse times A is the identity, and also A times A inverse is the identity. So I say n by n here. I mean, if I just say this, if A is a matrix, and this works, the only way that that could possibly happen, is the only way to multiply two matrices both ways is if they're both square. And so just going to point it out. If A is a square matrix, and it only works for some square matrices. In fact, I'm just going to rub that out. It only works for some matrices, some square matrices. And I already said in the other video that there is a number that we can calculate from our matrix that will tell us whether it has an inverse or not. And that number is called the determinant. And when it works, the matrix is called invertible. So if A has an inverse, then A is called invertible. And also, we can calculate the determinant, which is det A, or the determinant of A. It looks like an absolute value, but it's not. We don't read it like that. It's a number calculated from the matrix. And we know that A is invertible when det A is not 0 and A is not invertible when det A is 0. So this is the information we have so far. So we have a matrix we can find. Well, we don't know if we can find it, but we have some matrices have another matrix called the inverse, such that when you multiply them by the original, you get the identity. And only some matrices have them, and only the ones that are square, and not all the square ones have them. And sometimes they're called, and if you can find one, it's called invertible. And there's this number we can calculate from a matrix called the determinant, which if it's 0, there won't be an inverse. But if if there's 0, there won't be an inverse. And if it isn't 0, then there will be an inverse. Okay, so the big question that wasn't answered in the previous video was, how do you find the inverse? We know how the inverse interacts with various other bits and pieces, multiplication and that sort of thing, but what we don't have is how to find it. So there are 3 ways that we can find a determinant. One is using the adjoint or adjugate. 2 is using row operations, and 3 is constructing it from the determinant, from the inverses of other matrices that we already know. So I'm going to show you all 3. The last one's only going to happen very rarely, because rarely do you have your matrix made out of other matrices. So that's the big question, how to find them. How to find inverses. So our first way is going to be using the adjugate. So adjoint is what it's usually called in Australia and probably the USA. Adjugate is what it's usually called in Europe. And I like to call it adjugate because adjoint has another meaning in other areas of maths, but adjugate only has one word. So how to find inverses using the adjoint or adjugate. Now, this process will work for any sized matrix, but I'm only going to show you how it works for a 2 by 2. But it is possible to reconstruct how this works for different for really big matrices. It's just that it becomes really, really difficult to do for larger matrices. So I'm only going to show you for 2 by 2. Okay. So here we go. Let A be A, B, C, D like that. Now, if the determinant of A is not 0, then A has an inverse, and the inverse is 1 over the determinant of A times this matrix. And this matrix, you switch the A and the D, and you minus the B and the C. So you switch the entries on the main diagonal, and you minus the entries, the other 2 entries, without switching them. So we don't switch these 2, we just minus them, and we switch these 2, but keep them the signs that they currently are. And when I say minus, it's not like you turn it into something that is negative. If it's already negative, you'll do the minus, and that'll make it positive. Okay. So that's the thing. And just for your information, this thing just here, that matrix there is called the adjugate of A. Or if you like, Adj A. And the adjugate of A for bigger matrices is a lot more complicated to calculate. You don't just switch things on the main diagonal and minus everything else. For a start, if you had a 3 by 3, what does it even mean to switch the main diagonal? For a 3 by 3, every entry will be calculated from the rest of the matrix. So for a 2 by 2, what you put in this position is calculated from the whole rest of the matrix, except for that bit there, and so on. And so for a 3 by 3, it's a lot more complicated than that. And so that's why I'm not even going to show you. But just so you know, this is called the Adjugate, and if you ever see a method using the Adjugate for larger matrices, you know, feel free to use it, but it's not actually as easy as the later method I'm going to show you. So that's how to do it. And if the determinant isn't 0, you would never even write this because you can't do 1 over 0 and it doesn't even mean anything. So I'm going to do an example of finding an inverse and then just checking if it really is the inverse. I'm going to mix it up and call my matrix C. Find C inverse if C is, well, I don't need the is, if C is equal to this matrix. Okay, minus 5 a third on the top and 6 0 on the bottom. So first I need to find the determinant of C, and if that's not 0, then I can do this. So the determinant of C is minus 5 times 0, minus 6 times a third, which is minus 2. So since that's not 0, there is an inverse, and so therefore I can say, therefore C inverse is 1 over minus 2, because it's 1 over the determinant. And I switch these two, and I minus these two. And just to be complete, 0 divided by minus 2 is 0. Minus a third divided by minus 2 is plus a sixth. Minus 2, 6 times 1 over minus 2 is 3, and minus 5 times 1 minus 1 over 2 is 5 over 2. Yep. And so that is what the inverse is. And just to check if it really is the inverse, it should be that C inverse times C is the identity. So let's see what C inverse C is. So that was, oh sorry, I've done C times C inverse. That should work as well. So that's C. C inverse is this. Let's see what happens, eh? So minus 5 times 0 is 0. A third times 3 is 1. 0 plus 1 is 1. Minus 5 times a sixth is minus 5 sixths. 1/3 times 5 over 2 is 1/3 times 5 over 2 is 5 sixths. So we get minus 5 sixths plus 5 sixths, which is 0. 6 times 0 is 0. 0 times 3 is 0, so we get 0 in total. 6 times a sixth is 1, and 0 times 5 halves is 0, so we get a 1. So yes, C inverse is correct. Okay. Now let me just give you one more example. Find B inverse if B equals 7, 2, minus 14. 7 minus 2, minus 14, 4. So first I'd calculate the determinant of B, and I would get 7 times 4 minus 2 times minus 14. So this diagonal minus this diagonal. And 7 times 4 is 28. And 2 times 14, minus 2 times minus 14 is also 28, which is 0. So B inverse does not exist. It would not be correct to write down B inverse equals 1 over this calculation here. So I'm just going to write it and then cross it out. It would not be correct to write B inverse equals 1 over 7 times 4 minus 2 times minus 14, 4, 7, 14, 2. That's how you would do it. You would switch these two and minus those two. But since this thing is 0 and you can't divide by 0, the thing you've written doesn't even exist. And so you're not supposed to write things down that don't exist. So you're not supposed to write this. You just have to find another way of describing the fact that it doesn't exist, which is the whole point of the determinant. Okay, so that's how to find a 2 by 2 determinant. The next thing you would want to do is to find bigger determinants, which you can do with adjugates, but it's difficult. And so I'm not going to show you how to do that. What I am going to show you how to do is a whole other process that makes it possible to calculate determinants using a thing called row operations. But before I do that, I'm just going to have a little interlude where you can actually find inverses if you know other inverses. If you construct a matrix out of other matrices and you know their inverses, then you can calculate the inverses of the matrix you've got. The inverse of the matrix you've got. So using inverses of other matrices. So the thing I want to say is that the process of creating an inverse interacts quite well with multiplication. So firstly, I'm going to say some rules. So A inverse is A. So the inverse of A inverse is A already. For any matrix that actually has one. Okay, that's useful to know. It's a useful thing to know, and we'll get to that in a minute. And that's how inversing reacts to itself. Inverses react very well to other powers, and it's because of this rule here. If you do the inverse of A times B, it has to be B inverse A inverse. So inverses do, the act of doing the inverse does in fact come in over A and B, but you have to reverse the order of the matrices when you do it. Transposers do the same thing actually. And you can extend this rule to A to the P, so A to some exponent to the minus 1 is the same as A inverse. So A exponent to the minus 1 is the same as A inverse to the P. That's useful to know. And what are the other operations we can do? A scalar multiplication. Number times A inverse is the same as 1 over K times A inverse. Now, every single one of these rules can be proven. I can actually do one of those proofs in a second because I think that's a useful thing to do. But just as an example, if I knew what the inverses of a couple of matrices were, then I could find the inverse of another matrix. So for example, if A is 1, 0, minus 2, 1, and B is 1, 5, 0, 2, then I'm not going to actually prove it. But A inverse is 1, 2, 1, 0. And B inverse is... No, I'm not going to... Can I just change this back to a 1? And B inverse is 1, minus 5, 0, 1. Okay, you can see the switching of the ones doesn't do anything, and the minusing of these, and the determinant is 1. Okay, so those two things here, find AB inverse. Well, I can find AB inverse because I know what A inverse and B inverse are already. So it's probably quicker to just go AB inverse is B inverse A inverse, which is 1, negative 5, 0, 1, 1, 0, 2, 1, which is 1 times 1 is 1, 2 times minus 5 is minus 10, so that's minus 9. 0 times 1 is 0, 1 times 0 is 0, minus 5 times 1 is minus 5. 0 times 1 is 0, 1 times 2 is 2, 0 times 0 is 0, 1 times 1 is 1. And so that's what AB inverse is. This might not seem very edifying, but I just wanted to make sure that you understood how this works. If you reverse if you do the inverse and you want to bring that in, you have to reverse the order. Okay. Prove that AB inverse is B inverse A inverse. This is an interesting thing. Mathematicians like proofs, and the proofs are a reason why things are true. So if I want to prove that this was true, I would have to use the fact of what inverse means. So this is saying that I need to show that when I want to know what the inverse of AB is, the thing I should use is B inverse A inverse. So what I should do is this. If AB inverse really is, even better, AB inverse will be, I don't know how to say it, but I'm just going to say it instead of write it. If this really was AB inverse, then when I times it by AB, it should come out to the identity. And when I times it by BA on the other side, it should come out to the identity. So, if it really is the inverse, I should be multiplying AB by this to see what I get. So, AB times B inverse A inverse is the same as this. And B inverse is the same as the identity. And AI is A. And A inverse is the identity. On the other hand, I should do it the other way as well. Okay, so that's the same as B inverse AB. And A inverse is the identity. And IB is the same as B. And B inverse B is the identity. And so since when I multiply this by AB, I get the identity on both sides, we're allowed to say, therefore, AB inverse is this matrix. And that's how a proof that something is a matrix inverse would work. You have to multiply the thing by the matrix both ways and see if you get the identity both times. And if you do, then it really is the inverse. Okay. So now I'm up to the last way of finding inverses. The way I just did there is more of an algebra sort of thing. Oh, I did miss a rule. I knew I'd forgotten one. Transposes is a thing we can do to inverses too. A inverse transpose is the same as A transpose inverse. I knew I'd forgotten one. Sorry about that. So that thing is more about finding inverses, and it's much more useful in a proof than anywhere else. Yep. So, yeah, I should say that A plus B inverses is not going to interact with that particularly well. It doesn't work with numbers, it doesn't work with matrices either. Okay, so the last method of finding inverses is using row operations. So, this is a very fancy process, and it uses a bit of theory, but first I need to tell you what a row operation is. So, matrices began life as representing linear equations, and there'll be a whole other lecture about that at some point. We can borrow from linear equations the things that we can do to those and do the same thing to the rows of the matrix. So that's where they came from. It's not the day to really describe why that is the way it is. We're just going to run with it. But there are operations you can do on the rows of a matrix that will transform it into another matrix that has similar properties. And importantly, the most important thing about row operations is that if you do a row operation of the kind that I describe here on a matrix, it won't change the fact that it's invertible. So if you do a row operation on a matrix that's invertible, the new matrix will still be invertible. And if you do a row operation on a matrix that isn't invertible, the new matrix will still be not invertible. And so we can tell if a matrix is invertible. Instead of calculating its determinant, we can keep doing row operations until we get to a stage where we can tell whether the matrix we get is invertible or not. Okay, so I should write some of that down. So a row operation replaces some rows with combinations of other rows. Okay? That's a little bit tricky to describe, so it's best to do it with an example. But there are elementary row operations will always have only 3 different types. Elementary row operations come in 3 flavors. So we might have, just for example, it's easier to do it as an example. We'll have some row is the same row as it is, plus, well, I can do it. Row I is row I plus some multiple of some other row. Okay? That's one of them. Another one, so this is like the new row I. Another one, the new row I is some multiple of the old row I. I don't even need the EG anymore. There are 3 types. And the last one is that the new row I and row J are the old row J and row I. So we swap them. These are the 3 elementary row operations. There are other kinds of row operations. So you could totally do row 1 is 5 times row 1 plus 6 of row 3 minus 7 of row 2. That's totally a row operation. It's not an elementary row operation. Okay? And you could switch all the rows around in all sorts of different ways, and that's a row operation, but it's not an elementary row operation. And so the theory goes that elementary row operations do not change whether your matrix is invertible or not. So elementary row operations do not change invertibility. And so what that means is that they are a useful way of telling what's going on. So let me just do an example of the three kinds of row operations. If I had a matrix like this, like that, and I did this row operation, my new row 2 is my old row 2 minus 6 of row 1. Then I would get this. And some people write them down on the side so they can be very clear about how it was working. So row 2 was this, 6, 7, 9. Minus 6 lots of row 1 was minus 6 times 1, minus 6 times 2 is minus 12, minus 6 times 7 is minus 42. And so when you add those two together, you get 0, minus 5, and wow, 9 minus 42 would be minus 33. So when I did this row operation, I didn't change row 1, and I didn't change row 4, but I did change this row here, and it's now 0, minus 5, minus 33. Okay? So that's one row operation that I could do. Another row operation I could do would be to multiply a row by something. And I notice all of these have a 2 in them, so I'm going to divide them all by 2. New row 3 is a half of row 3. So there's not technically a rule for dividing a row by something. It's just multiplying it by a constant, so I'm going to multiply it by a half. I didn't change row 1, I didn't change row 2, and I did change row 3. And the only other operation you would do, which is not actually, none of these at the moment are for any particular purpose, I'm just doing them to show you how they work, might be to swap 2 rows. So I might say that the new row 1 and row 3 is the old row 3 and row 1. So I didn't change row 2. The new row 1 is the old row 3. The new row 3 is the old row 1. Okay, these are the 3 kinds of row operations you could do. Okay, so you could imagine trying to do row operations to get as many zeros in place as you could so that you could tell if it was invertible. Actually, each of these row operations doesn't just maintain invertibility. You can keep track of exactly what it does to the determinant. So row operations are a pretty quick way to calculate a determinant of a big matrix. You can do row operations until you figure out what the determinant is. And importantly, a row operation like this doesn't actually change the determinant. So the determinant of this matrix is the same as the determinant of this matrix. Halving a row will halve the determinant, so the determinant of this one is half the determinant of that one. And swapping rows will minus the determinant, so the determinant of this one is minus the determinant of that one. So if you could keep track of what the row operations do to the determinant, you could find what the new determinant is if you wanted. We're not going to do that today. It's not a thing that's generally asked for in most high school courses, but it might turn up in a university course at some point. Okay. But there is a super cool magic trick that row operations do, and the super cool magic trick is that if we do row operations on the original matrix and do the same row operations on the identity at the same time, then by the time the original matrix becomes the identity will have become the inverse. It's a really cool trick. So a process to find an inverse 1, create a new matrix of A. A new matrix which is made by gluing together A and the identity. And that's how we normally write it on paper. Do row operations on this big matrix until A becomes I. And 3, then the new matrix is I next to A inverse. Now it's not like this whole thing is the inverse, just a little bit in there, that will be the inverse by that time. Okay, that's the process. So let me do some examples. And the reason this process works is it's actually possible for these to do these row operations, instead of by doing a row operation like this, it's possible to do them by multiplying a matrix on the left-hand side. And since row operations are really produced by matrix multiplication, if I'm able to multiply a whole lot of matrices by A to get the identity, then that product of matrices is the inverse. So it's a really cool proof that proves this, but it's sort of a little outside the scope and there's a little too much stuff going on to be able to prove that. I don't really want you to be able to turn your row operation into a matrix right now, so I'm just going to show you how this process works. Okay, so let's do an example. I'll do a 2 by 2 first. And in fact, why don't I do one of the matrices I already found? Here, this matrix C. Find C inverse if C is minus 5, 1/3, 6, 0. Okay. So I'll do it by this method, and you can compare for yourself which one you think is more efficient. I'm going to line it up next to this. Okay. And then I'm going to do row operations. So my goal is for this to be the identity matrix here. Well, the quickest way I know to get an identity matrix in that spot would be to I need to put a 1 here and a 0 here. Now, to get a 1 in this spot, I could divide, like I could times by minus a fifth, and that'd be okay. I could also add this onto there, and that would get a 1 in that spot as well, so I might do that first. So my new row 1 is my old row 1 plus my row 2. And so it's technically one of the proper elementary row operations, row 1 plus 1 of row 2. So let's see. I didn't change row 2. And then I added row 1 to row 2. I reckon I can do that one without actually writing out the working. Minus 5 plus 6 is 1. 1/3 plus 0 is 1/3. 1 plus 0 is 1. And 0 plus 1 is 1. So remember, you have to use the entire row of the whole matrix. Also, importantly, don't put an equals here, because this matrix is not equal to that matrix. The equal sign does not mean, and here is the result. It means this is the same thing as that thing, and they are not the same. It is just what you get when you do the row operation. So you don't write, write an equal sign there. Okay, so I have the one that I want. In my head, I'm thinking at the moment about this column, and thinking I would like it to be 1, 0. And so now here I am. I have the one that I want, that's good, and I need there to be a 0 here where the 6 is. And I can't go multiplying a row by 0. I'm not allowed to do that, and I should probably go back to my row operations and say that k is not allowed to be 0. K is allowed to be 0 in this one, because if k is 0, you're just not doing anything. Okay. So I need a 0 in that spot. I'm not allowed to multiply by 0. Switching rows isn't going to help. I just made a 1. That was what I needed to do. So the only thing I can think of is to go this row minus 6 of that row, and that would produce a 0 in that spot. And one of the reasons to make a 1 first is that you can always do that trick. Okay, so let's go. My new row 2 is my old row 2 minus 6 of row 1. Okay, and so I have, now this is what the old row 2 was, 6001, and this is minus 6 of row 1, which is minus 6. Minus 6 times a third is minus 2, minus 6 times 0 is still 0, and that's minus 6. Then I add them together, and so what I've got is I didn't change row 1, and this became 6 plus minus 6 is 0, 2 plus, let's just do it, 0 minus 2, 0 minus 5. Okay, so now in this first row I have the 1 and the 0 that I want. That's good. And now I'm going to move to the next column. And in that column I would like there to be a 0, 1 because I've already got the 1, 0. So I can't go putting a 0 in this spot, you know, by multiplying by 0. I could times this by minus a half, and so that's what I'm going to do. So my new row 2 is minus a half of row 2. That would put a 1 in the spot where I want it. So I didn't change row 1, but I did change row 2. There we go. Looks like we're getting closer to the inverse that we were hoping for. And now I would like to have a 0 in this spot. And so I will go, my new row 1 is the old row 1 minus a third of row 2, because a third minus a third of 1 is 0. And so let me just think, row 1 is 1 a third 1, 1. Minus a third of row 2 is 0 minus a third, 0 minus 5, 6. Okay, and when we add them together we get 1, 0, 1. 1 minus 5, 6 would be a sixth. Okay, and so we have, we didn't change row 2, but we did change row 1. And hopefully that's the same as the inverse we found last time. There's a 3 in this spot which I didn't expect. Just a second. Let's just go back and see if we've got this right. Oh, look. I did this wrong. I went along here and then skipped down here. So it's minus 6 of row 1, that's minus 6. Minus 6 of row 1 will be a minus 6 there. That'll make that a 6 in this spot. Okay, and so if that's a 6 in that spot, when I do minus a half of row 2, oh no, that's a minus 6. It's 0 plus negative 6. Okay, when I go at minus a half of row 2, that'll be a 3 by that spot, which means this is a 3. Be a minus 1, which means there'll be a 0 here. Right, and we can see if it's working correctly this time. So the original, right, that row is this row. All right, the original matrix was this. So if we have minus 5 times this, oh no. No, it's all looking good. Minus 5 times 0, a third times 3, that'll be 1. Minus 5 times a 6 is minus 5, 6. A third times 5 halves is 5, 6, so they cancel. 0 times 6, 0 times 3. 6 times 1, 6 is 1. 0 times 5, 2 is 0. Okay, it really does work. I have checked that it really is the inverse, and so therefore I've done it right. And in fact, if I had done that check earlier, even if I didn't already know what the inverse was, that would have told me something was wrong, and I could have gone looking to see that somehow I did I had multiplied the wrong row. Okay. So I can do it for a 3 by 3 just as much as I can for a 2 by 2. So, for example, find the inverse of this matrix. Give me a second. This matrix here. Okay. So what I'll do is I'll line it up next to an identity. And I will do row operations until the left-hand part is the identity. And then by that time, the inverse will be that. Actually, I didn't finish the previous one. I'm sorry. The only way to finish this wasn't finished. I was told to find what C inverse is. I need to say, so C inverse is this matrix. Right. Question isn't finished until you answer the original question. Because this isn't the inverse, just that bit is the inverse. Sorry about that. Really not doing well with my paying attention today. Okay, so let's do the row operations and let's make sure that we do all the things that we're supposed to do. So I need a 1, 0, 0, and I'm going to do it one column at a time. So I need that to be 1, 0, 0. It already has 2 zeros in it, so the quickest way is probably to swap 2 rows to get the zeros in the right spot. So if I swap row 1 and row 2, then I'll have something 0, 0, and it'll be nearly the way I want it to be. Okay, so let's do my new row 1 and row 2 are my old row 2 and row 1. So I didn't change row 3, and this is the old row 2, and this is the old row 1. Beautiful. And so now I need a 1 in this spot here, so I'm going to multiply that one by -1. So the new row 1 is minus the old row 1, because that's the same as multiplying by a number, so that's okay. So I didn't change row 2, I didn't change row 3, and the new row 1 is minus the old one. Okay. Doing well. And so now what I want to do is I've got my first row column as the identity matrix column. So let me look at the next column. I would like there to be a 1 in this middle position. And I can do that by swapping rows, actually. So I might do that. So my new row 2 and row 3 is my old row 3 and row 2. And so my matrix has become, row 1 didn't change. This is now 0, 1, 8, 0, 0, 1, and this is our 0, 5, 8, 1, 0, 0. Okay, and now let's see, we've got a 1 in the correct position, and we need there to be the zeros above and below it to get my middle column of the identity. Okay, that's cool. So I'm going to need to do row 1 is row 1 plus 2 of row 2. That would put a 0 in that spot. And then I'm also going to have to do row 3 is row 3 minus 5 of row 2. That'll put a 0 in that spot. Now, it is possible to do 2 row operations at a time, but only in that situation. Only in the situation where the rows that are changing aren't being used to then change another row all in one step. So since row 2 isn't going to change, I can use it to affect both of the others. Pardon me. So let's see. My new row 1 will be my old row 1 plus 2 lots of row 2. And my new row 3 will be my old row 3 minus 5 lots of row 2. Okay, so let's see. Row 1 is 1, negative 4, negative 2, negative 4, 0, negative 1, 0. And row 2 is 0, 2, 16, 0, 0, 2. So when I add them, I get 1, 0, 12, 0, negative 1, 2. So that's my new row 1. And so we also have row 3 was 0, 5, 8, 1, 0, 0. And minus 5 of row 2 is 0, minus 5, minus 40, 0, 0, minus 5. And so my new row 3 is 0, 0, 8 minus 40 is negative 32. 1 minus 0, 0 minus 0, 0 minus 5 is minus 5. Okay, and so my new matrix is now 1, negative 2, negative... No, just a second. My new row 1 was 1, 0, 12, 0, negative 1, 2. My new row 3 was 0, 5, 8, 1, 0, 0. And my new row 2 is the old row 2, 0, 1, 8, 0, 0, 1. Okay. Oh, this isn't a 0, 5. I just copied it again. What am I doing? This is the new row 3. 0, 0, negative 32, 1, 0, negative 5. Just let me check. Yes. Yes. Okay. Right. So I've got the first column, which is the identity. I've got the second column, which is the second column of the identity. I need this to be the third column of the identity. Okay, well, the only way I'm going to be able to put a 1 in that bottom spot is if I divide by minus 32, which is only mildly distressing. So really, excuse me, I'm just going to have to do it. Okay. My new row 3 is minus 1 over 32 times row 3. 1, 0, 12, 0, negative 1, 2, 0, 1, 8, 0, 0, 1, and 0, 0, 1, minus 1 over 32, 0, 5 over 32. Okay. So now I'm going to do, I'm going to clear these two. So I'm going to do new row 2 is the old row 2 minus 8 of row 3. And I'm going to do new row 1 is the old row 1 minus 12 of row 3. All right, this is where I'm really going to need to do this working. So row 2 is 0, 1, 8, 0, 0, 1. And minus 8 of row 3 is 0, 0, minus 8. Now minus 8 over 32 would be 8 over 32, which would be a quarter. That's fine. Minus 8 times that would be minus 5 quarters. And so my new row 2 is 0 plus 0, which is 0, 1 plus 0, which is 1, 8 plus minus 8, which is 0, 0 plus a quarter is a quarter, 0 plus 0 is 0, 1 plus minus 5 quarters is minus a quarter. Beautiful. So that's my new row 2. Now the old row 1, I could actually put an equals there because it really was old row 1, but whatever. The old row 1 was 1, 0, 12, 0, negative 1, 2. Minus 12 of row 3 was 0, 0, minus 12. Whatever 12 on 32 is, 0. And whatever 5 lots of 12 on 32 is. Okay. I'm just going to figure that out. 0, 0, minus 12. 12 on 32, we could divide both of them by 4, and that'll give me 3/8. I could divide both of these by, and that's still 3/8. And so that'd be 15 over 8. Okay. And the 2 would be 16 over 8, wouldn't it? Just to make my subtraction a little easier. So let's see. 1 minus 0 is 1. 0 minus 0 is 0. 12 minus 12 is 0. 0 minus 3/8 is minus 3/8. Minus 1 minus 0 is still minus 1. 2 minus, so 16/8 minus 15/8 is 1/8. And so I get that my new matrix is, I didn't change row 3, so it will be the same as it was before. And I changed row 2 to 0, 1, 0, 1 quarter, 0, minus 1 quarter. And I changed row 1 to 1, 0, 0, minus 3/8, minus 1, 1/8. And so I have the first identity column, the second identity column, the third identity column. Everything is working as it should. And so the inverse of this matrix should be this. One quarter, 0, minus 1 quarter, 1 over 32, 0, 5 over 32. Okay, and if we want to check if this really works, we're going to have to multiply the original matrix by this. So let's see. So let's see. 0 times minus 3/8 is 0. 5 quarters minus 8 on 32. Well, 8 on 32 is 1 quarter, so we have 5 quarters minus 1 quarter is 1. Okay, so that's working well. 0, 0, 0, beautiful. 0, 0, 0, beautiful. So my first row is correct. Minus, so plus 3/8 plus 2 quarters. 2 quarters is a half. So that's 7/8. So plus 3/8. Well, something's going wrong here. So minus 1 times minus 3/8 is 3/8 plus 2 quarters, which is 4/8. So I have 3/8 plus 4/8 is 7/8. Minus 4 over 32, which is 1/8. So 7/8 minus 1/8 is not 0. Something went wrong somewhere. I'm just going to check with my calculator that I'm doing that calculation correctly, because with fractions I can get it a bit wrong. So let's just check that. Minus 1, minus 1, times minus 3/8. Just a second. Minus 1 times minus 3/8. Plus 2 times 1/4. Plus 4 times minus 1/32. 0.75. 3/4. Okay. So, something is wrong somewhere. I'm going to have to go back and find it. So my first row is okay. Well, actually, it's more like my first column is bad, isn't it? If I went along, when I went along this row and did all three of them, that worked correctly. So I really should have done them, since I did these by rows, I really should have done them one row at a time. It would have been much more productive to do it this way, to try and figure out which row was the problem, because it's probably the rows that are the problem. So 0, 1, 0, that's correct. Minus 15/8, minus 2, plus 1/8. My top row is wrong, isn't it? Could have been anywhere. Okay. So I do know a neat little trick is that if I do the thing here on the left of my original matrix, it should produce this thing here. So that should be true everywhere. So if I go back to an earlier stage of my working, okay, let's see. 0, 1, 0, beautiful. 0, minus 1, minus 2 plus 2, that does produce a 0. 8, minus 4, plus 16 is 12. Okay, so just a second. This top row was correct at the time. I think it was my very last row operation. It was my very last row operations that I did wrong. Let's see if I can find it. Very last row operation was wrong. Okay, so first I'm going to check if I copied them down correctly. So I do need to do row 2 is row 2 minus 8 of row 3, and row 1 is row 1 minus 12 of row 3. Beautiful. So row 2 is 0, 1, 8, 0, 0, 1. Yep. And minus 8 of row 3 minus 8 of row 3, 0, 0, minus 8, 8/4, 0, 0, minus 4/4. That seems reasonable. But it was row 1 that was the problem, wasn't it? So let's see. 1, 0, 12, 0, minus 1, 2. Yep. Minus 12 of row 3. 0, 0, minus 12. Yep. Well, I have to do 12 on 32. That's right. It's a minus here. We were multiplying by minus 12. Right. It was a minus sign. So this becomes minus 15/8. And when I go 2 plus minus 15/8, that's 16. Wait, just a second. I was supposed to add them anyway. I thought I was subtracting them, but it's already got a minus, so I have to add them. 1 plus 0 is 0. 0 plus 0 is this. So 12 plus minus 12 is this. 0 plus 3/8 is 3/8. Minus 1 plus 0 is minus 1. And 2 plus minus 15/8 is 1/8. And so it's this one that's supposed to be a plus 3/8 here and here. Right, let's do our multiplication and make sure it's working the way it should this time. Okay, 0, 1, 0. Okay, beautiful. That adds up to 1. 15/8 minus 2, which is 15/8 minus 16/8, which is minus 1/8, plus 1/8 is indeed 0. 3 minus 4 is -1, plus 1 is 0. A quarter, so 0, 0, 0, beautiful. 0, 0, sorry, 5 quarters plus 0 minus a quarter. 5 quarters minus 1 quarter is 4 quarters, which is 1. Okay, that's working well. 2 plus 0 minus 2 is 0. 0, 0, 0. Okay, cool. 5 minus 5 on 32 plus 0 plus 5 on 32 is 0. And this last one should be 1 minus 8 on 32, which is minus a quarter, plus 0, plus 5 lots of 8 on 32, which is 5 quarters. 5 quarters minus a quarter is 1. It really does work. And so, yes, I have found the actual inverse because I've done the multiplication. So since this multiplies by the original to give the identity, it is correct. So I should say that if you're ever given a maths assignment or an exam where you're asked to find an inverse, there is no excuse to hand in something that's wrong, because you can always check it yourself. And so if you've checked it, you will be able to go and find the answer. And there was a strategy I used that at any stage of the process, if you multiply the original matrix here on this side of the thing over here, it will always produce the thing that's there. So if I multiply put this here, it will produce that answer. If I put this here, it will produce that answer. And it works at every stage, and in particular it works at the final stage, and that is why it works the way it does. So that's how to find inverses, and thank you for listening.